Understanding its importance. The scientific method is a systematic way of exploring the world around us. It's like having a reliable roadmap for discovery. At its core, this method helps us separate facts from opinions, which is crucial in our quest for knowledge. So, why is the scientific method so important? Well, it keeps things fair and objective. In our daily lives, we encounter countless claims and theories about how things work, from why the sky is blue to how a new medicine can heal. The scientific method ensures that we don't just take these claims at face value. It's like a quality control process for ideas. For students, understanding the scientific method is like unlocking a secret code to critical thinking. It's a tool that goes beyond science classes. Once you grasp it, you'll find it useful whenever you encounter a problem that requires evidence-based solutions. It's about learning to ask the right questions and finding reliable answers. When scientists use this method, they start by making observations. Imagine you notice that plants tend to grow towards the light. Interesting, right? The next step is to ask a question. Why do plants do that? From there, you'll form a hypothesis, which is a fancy word for your best guess or explanation. Maybe you think plants grow towards the light because they need it for energy. But it doesn't stop there. The next stage, experimentation, is like setting up a fun mini-adventure to test your idea. You could put a plant in a box with a light at one end to see if it grows towards the brightness. Based on your findings, you'll draw a conclusion. If you're right, awesome. If not, that's okay too. Science is about learning from every result, even the unexpected ones. The scientific method isn't just for scientists in a lab. Think about a detective solving a crime. They gather clues, observation, develop theories about who did it, hypothesis, and then look for evidence to prove or disprove their theories, experimentation. So whenever you're solving problems, whether it's a puzzle or a bigger mystery, you're using the same process. Historical context and evolution. The scientific method may sound modern, but it's been evolving for centuries. Its roots go way back, intertwined with the work of clever thinkers trying to understand the world. In ancient Greece, philosophers like Aristotle laid the groundwork. They believed in observing the world and using reason to make sense of it. Although their approaches weren't as structured as today, they set the stage for what would come later. Fast forward to the scientific revolution, which kick-started in the Renaissance. This era was all about breaking free from old ways of thinking. Figures like Galileo Galilei and Sir Isaac Newton championed the idea of using experiments to test theories. They were like the rebels of their time, shifting reliance from authoritative texts to empirical evidence. The 17th century saw the method take a more formal shape. A key player in this journey was Sir Francis Bacon, often called the father of empiricism. Bacon proposed a systematic approach, where gathering data and making observations led to forming hypotheses and conducting experiments. As time went on, the scientific method continued to adapt. In the 20th century, philosopher Karl Popper introduced the idea of falsifiability. He argued that scientific theories should be framed in a way that allows them to be tested and proven wrong if necessary. This concept was a game changer. It meant that science wasn't just about proving things right, but also about having the openness to challenge and improve them. The evolution didn't stop there. Today, with technology and interdisciplinary research, the scientific method keeps growing. It's more dynamic and accessible, inviting anyone with curiosity to use it. From fields like physics and chemistry to social sciences and medicine, it's the backbone of inquiry and discovery. Understanding this history helps us appreciate the scientific method's strength. It's not just about the layers of experiments and data. It's about a journey that has refined how we search for truth. This journey shows us that asking questions and seeking evidence have always been vital parts of human nature, driven by a desire to understand the mysteries around us. In a world where information is abundant and sometimes unreliable, the scientific method shines as a beacon of clarity. It's a protective shield against misinformation, reminding us that truth is not just what seems believable, but what can be consistently tested and verified. So, as students, as future innovators and thinkers, Embracing the scientific method is about more than a Kinga science test. It's about nurturing a mindset geared toward curiosity, skepticism, and a relentless pursuit of understanding, traits that have pushed humanity forward for centuries. By understanding the scientific method's importance and history, you're not just learning a topic segmented in science textbooks. You're stepping into a long tradition of wonder and inquiry, a path tread by some of the greatest minds. It's your invitation to join the exploration, to wonder, ask, test, and discover the world anew each day. Key steps in the scientific method. Observation and research. All right, let's dive into the first step of the scientific method. Observation and research. Imagine you're a detective trying to solve a mystery. What's the first thing you do? You gather clues. In science, this means observing the world around you and collecting information about your topic of interest. It's like being really curious and asking, what's happening here? During this stage, you might notice patterns or unusual happenings. For instance, you might see that plants in your garden grow faster in one spot than another. This sparks a curiosity that leads you to ask questions and start digging deeper for information. You can read books, check out scientific articles, or explore online resources to gather relevant data. This research phase is all about getting a solid understanding of what's already known, which sets the foundation for your next steps. Formulating a hypothesis. After gathering enough information, it's time to formulate a hypothesis. Think of a hypothesis as an educated guess, your possible explanation based on the observations you've made. It's like predicting who ate the last cookie in a family of 5, but with more science and less finger-pointing. A good hypothesis is specific and testable. It should address the variables involved. For example, if you observed that certain plants grow better in sunlight, your hypothesis might be, if a plant receives more sunlight, then it will grow faster than a plant that receives less sunlight. This statement sets up a cause and effect relationship that you can test through experiments. The key here is that your hypothesis should be something you can verify or refute with data. Conducting experiments. Here's where the fun really begins. Conducting experiments. This step is like the moment in a cooking show where all the ingredients come together to make something amazing. In this part, you design and carry out experiments to test your hypothesis. It's crucial to plan carefully and decide what variables you will change and what you will keep constant. Let's continue with our plant example. You might set up 2 groups of plants, one that gets plenty of sunlight and another that receives minimal sunlight. Everything else, like water and soil, should remain the same in both groups. This way, you can say with more confidence that any differences in growth are because of sunlight, not something else. Conducting controlled experiments helps ensure that your results are reliable and consistent. If the plants in the sunny spot grow faster, your hypothesis is supported. But if they don't, it's back to the drawing board. Analyzing results. Once you have your data, it's time to roll up your sleeves and dive into the fun task of analyzing results. This step involves looking at the data you've collected from your experiments and figuring out what it all means. You might use graphs, charts, or statistical analysis to make sense of the information. This stage is like being a detective who has gathered a bunch of clues and now needs to piece them together to solve the case. You're looking for trends, patterns, or anomalies that help answer your original question and support or refute your hypothesis. If our plant experiment showed that plants in more sunlight grew consistently taller, you could solidly claim a pattern. Just be sure to check for any experimental errors or biases that might have skewed the results. Drawing conclusions, finally. Drawing conclusions wraps everything up nicely. After analyzing the results, you come to this step where you figure out what the outcomes mean in the context of your hypothesis and original question. This part is like writing the final paragraph of a mystery novel, where everything comes together and the mystery is solved. Your conclusion will tell you whether your hypothesis was correct or if it needs some tweaking. Using our plant example, if the sunlight truly made the difference, your conclusion might support your initial hypothesis. If the results didn't support it, that's all right too. Science often involves trial and error. and every finding adds to our understanding of the world. Finally, you share your findings with others. Whether through a written report, a presentation, or a blog post, communicating your results helps others learn and build on your work. And who knows? Your study on plants might inspire other budding scientists to explore even more facets of nature's wonders.